Okay, so welcome to our session for today. We are going to have problems on flexural stress. So in this problem, we have a cross-sectional the member is having a cross-section of 150 by 200. So we have a z and y-axis. We are going to determine the maximum stress on the layer of z and the layer of y. So the member is to resist a bending moment of 90 kilonewton meter. So first and foremost, we would want to recall the formula of flexural stress. So it is given by this formula m over I is equal to sigma b all over y is equal to the modulus of elasticity all over the rho or the radius of curvature. So this formula will be cut down into this side and this side because it involves the cross section of the member, so we do not need to express it in terms of this right portion here E all over rho because we do not have any modulus of elasticity as well as the radius of curvature. So we use this and then we cross multiply. We have my all over I. So please take note that y here is the distance of the layer from the neutral axis. We also note that the unknown here is about the maximum stress. Okay, so we will be considering the greatest or the farthest distance of y from the neutral axis. And that farthest distance is what we call C. So if maximum C is the farthest distance from the neutral axis, hence our formula becomes flexural stress maximum is equal to mc all over I. So I is the moment of inertia, wherein in this problem it involves a rectangular shape. And we recall the formula for rectangular shape. Inertia is equal to bh cubed all over 12. So we now consider the cross section at the layer of first we consider the layer z, or we shall call it at the z axis. So at the z axis we have the cross section where the base is 200 and the height is 150, so that we can derive its height. We have 200 as the base, 150 as the height, so we divide it by 12. We have 56.25 millimeter times 10 raised to 6 millimeter raised to 4, and this shall be the I for the z axis. And for the y-axis, it will just interchange your dimension. Say this is the y-axis, so therefore your base becomes height and your height becomes the base. So we have this expression, and so from this we can now employ the formula for maximum bending stress, wherein the bending moment should be 90 kilonewton meter. So when using this formula, we must have to be consistent. Remember that your moment is in terms of 90 kilonewton meter. So we apply it for z-axis first. We note that the farthest distance is equal to 75 millimeter if we consider our upright height is 150, and the farthest distance if z is to be considered. So it so happened that the z-axis axis having this orientation. Okay, so we'll just have to substitute the values, and for the moment that is 90 kilonewton meter, we have to multiply 1000 to make kilonewton in newton, and another 1000 makes 20. We are actually multiplying here 1 million to our 90 from kilonewton meter to make it in Newton millimeter. So we multiply the C, 75, and the moment of inertia. So we'll be having an answer of 180 megapascals. Okay, so we do the same for the y-axis. So we have this value C is equal to 100 up to we have C of cancel 100 with the maximum of 90 megapascal for y-axis. Okay, so that's it for this problem. Okay, so moving on to this problem, we have here a T-beam with the following dimensions. Of course, this is subjected to a moment of 4 kips per feet. We're going to determine the maximum tensile and compressive bending stresses. So first and foremost, we need to know what is the orientation of this beam. So what will be our basis? Our basis is on this moment applied on the cross section. So when this moment is applied to this cross section, the orientation is obviously concaving upwards. So the fiber is concaving upwards. Why? Because the value for the moment is a positive value. So if we have a bending, therefore there will be two zones here where the neutral axis will be our boundary. So beyond this neutral axis, it could be either tensile or compression zone. So in this case, the elements that are being stretched here are the ones below the neutral axis. And this one is the tension zone. And the fiber above should be the compression zone. So meaning all elements are being compressed. So of course, before we can proceed with the calculation, we need to locate our neutral axis so that the distance for T can be utilized as well as the distance for the compressive zone. So in order to do that, the first step in the procedure is to have a reference line within this cross-sectional area. You can either consider the topmost fiber as your reference or the bottom fiber as your reference or anywhere in the beam. And in this case, I'll just consider the bottom fiber as my reference to measure where is the y-bar. So y-bar is actually measuring the neutral axis from your reference line. Say that is your neutral axis. And then we start to have this procedure wherein the total area is multiplied by y-bar and equated to the summation of a times y of all of the shapes involved here. So of course we would want to divide or subdivide the total shape into composite shape. So for me, I'll just divide it this way and then label all the composite shapes. Say I have number 1 for these two shapes, identical shapes, and we have here the 2 and then the third shape. So all are rectangles. Then we compute the area 1. Area 1 is equal to 3 by 0.5 and that is equal to 1.5 square inches for a single composite area 1. And its y is the distance of the centroid of this composite area from your reference line. And what is that? From the centroid of this small rectangle up to your reference line is actually y1. That is, half of 3 is 1.5 plus Let us try to correct this as 7 inches because this is measured from this up to this as 10 and this is measured as 3, so therefore this should be 7 inches. So getting the value of y1, we have 1.5 plus 7. So that is equal to 8.5 inches. We place it here. And then for A2, we have 4 by 0.5 or that is equal to 2 square inches. And for the distance, y2, we have this point up to your reference line is actually equal to 1 y2. And that is 7 plus 3, 10, plus the half of 0.5, that is 0.25. So basically we have here 10.25 inches. We place it there, and then for the third area we have 10 by 0.5 and this is 5 square inches. And then for y3, we consider the centroid of this third composite area up to your reference line, and that is actually the half of 10. So we place it here. Y3 is equal to 10. Then we calculate the total area from this. Of course, 1.5 should be multiplied by 2 so that this becomes 3, or 1.5 times 2 is equal to 3 square inches. So we add all of those. We have 3 plus 2 plus 5 is 10 square inches. So we write the formula 10y bar, and then area 1 should be 2, or 2 areas. We multiply that by 2. And the area 1 is 1.5 times 8.5 inches plus area 2 of 2 times 10.25 as y2 plus area 3, 5 times y3, 10. I think we have miswritten your y3 here, so y3 is 5. So calculating y bar should be 7.1 inches. So if we have calculated y bar, we are now ready to determine what is the farthest distance of the compression zone as well as the tension zone. So the tension zone is at the bottom, which is actually y bar 7.1. Therefore, this top distance here is 10.5 less 7.1. We have an equivalent of 3.4 for that. Okay, so we cannot proceed further if we do not know the centroidal moment of inertia, which is actually I bar x, which is given by the formula summation of I plus AD squared. So what are these? These are actually the I and the area and the distance, or the D is transfer distance of this composite area. So all in all, we have 3 composite areas wherein 2 are identical. So before we proceed with this formula, we need to determine the transfer distances of those composite areas. Okay, for area 1, we have the centroid up to the neutral axis, that is D1. And then the centroid of 2 up to the neutral axis, that is D2. And the centroid of the shape 3, or the rectangle 3, is D3 up to the neutral axis. So we now compute for D1. So we take the distance, 3.4 minus 0.5, so it becomes this one, minus half of 3, 1.5. So 3.4 less 0.5 less half of 3, which is actually 1.5, that equates to our D1, which is 1.4 inches. Okay, for D2, we have this one. So we have 3.4 less half of 0.5. Okay, half of 0.5. So 3.4 less half of 0.5, that is D2. So we have 3.15 inches for D2. And then finally for D3, we have to consider the bottom dimension or y bar from the bottom, that is 7.1. Okay, minus half of 10, that is 2.1 inches. Okay, for an alternate solution, you may do it as subtracting your computed y bar with the corresponding y's. Okay, so what is our y bar? 7.1. We have negative 1.4. So the y bar minus negative or 7.1 minus 10.25 is equal to negative 3.15. And D3 is equal to 7.1 minus Y3, which is 5. That is equal to 2.1. So these are the distances which came from your reference axis. And this is Y bar, which is also measured from the same reference axis. So if you notice, we'll have the same value. However, there are negative signs here, but it does not matter because in your formula, D is just simply squared here. It will just eliminate the negative sign. Okay, so this is the alternate solution for D1, D2, and D3, or solving for the transfer distances. So we are now ready to determine our I bar X. We have two areas for the 1, a single area for 2, and I plus AD squared for 3. So substituting the values, we have 2 times 0.5 by 3 cubed all over 12 plus 1.5 for area 1 times 1.4 squared plus 4 times 0.5 cubed for 2 all over 12 plus 2 times 3.15 squared. Okay, and then for the third one, we have plus, what is the third one? Base is 0.5, height is 10. So BH cubed all over 12, the area is 5, and D3 is 2.1, and that is squared. Okay, so calculating the value, so we must have to be careful. I bar X is equal to, we have 91.73 inches raised to 4. Okay, so we can now have the maximum stresses on the compression and the tension if this has to carry a certain moment. And the moment is equal to 4 kips per feet. So basically, we'll just have to substitute it in our formula. Okay, so our formula here is sigma bending is equal to MC all over I. So we'll just have to see that for tension, the tension side is at the bottom, and the farthest distance of the tensile zone is actually 7.1. We can place it here. C is equal to 7.1, and then sigma bending is equal to 4 kips. So the unit is kips per feet. So we need to express this into inches first. Wherein we must have to divide it by 1 over 12, okay, to make it in kips per inches. So we multiply it by the distance, or 7.1, divided by the computed I in terms of inches. Okay, so we have sigma b in tension. Okay, so let us check our units first for a moment. I think you should express your moment in kips feet, so that your multiplier should be 12. Okay, so because 1 foot is equal to 12 inches, you just have to replace that one. So it's 12. So our answer here is in terms of inches. Okay, so we're going to yield with 3.72 ksi, and for your compression side, we have the value for C for compression side is 3.4. So place it there and then just replace this. And this one. So if we compute that one, we arrive at 1.78 ksi. Okay, so those are the stresses, or the bending stresses on tension and compression zone. So if we notice that the solution is more on the determination of I and the transfer distances, as well as the centroid of the cross section. So let us stand by for another problem. Thank you for listening.